Let's look at another example. We're trying to balance the equation for the combustion of butyric acid. Since this is another combustion reaction, O2, CO2, and water are part of the equation. We're going to approach this in the same way as balancing the equation for the combustion of propane. We're going to balance the carbons first by putting a coefficient in front of the CO2. We'll balance the hydrogen second by putting a number in front of the water. We'll balance the oxygens last by putting a number in front of the O2. In this case, it's a little trickier than before because we have oxygen in two different types of molecules on the left side of the equation. It's part of the hydrocarbon in addition to being by itself in the O2 molecule. Our first step is listing how many of each type of atom we have on each side of the equation. On the left side, we have 4 carbons, 8 hydrogens, and a total of 4 oxygens, 2 from the hydrocarbon and 2 from the individual molecule. On the right side, we have 1 carbon, 2 hydrogens, and a total of 3 oxygens. In fact, for all of our combustion reactions, we're going to have 1 carbon, 2 hydrogens, and 3 oxygens to begin with, because our combustion reactions will always have CO2 and water on the right-hand side. We're going to start adding in coefficients, first in front of the CO2. Since we have 4 carbons on the left, we need 4 carbons on the right to balance it out. We're going to put a 4 in front of the CO2. That also updates our count for our oxygens. We have 4 times 2 is 8 from the CO2, plus 1 from the water makes 9 oxygens on the right-hand side. We put a 4 in front of water in order to make the hydrogens match up. There are 8 hydrogens on the left, so we put a 4 in front of the water so that we can have 8 hydrogens on the right. But this also changes our number of oxygens. We have 4 times 2 is 8 from the CO2, plus another 4 from the water makes 12 oxygens on the right. Since we have 12 oxygens on the right, we need to have 12 oxygens on the left, but they're not all going to be from the O2 molecule. Some of them will be coming from the hydrocarbon. We're going to assume that we're going to keep the understood coefficient of 1 in front of the hydrocarbon, because if we were to change that, then the 4 in front of the CO2 and the 4 in front of the water would also have to change. If we keep the hydrocarbon's coefficient as a 1, that means 2 of our oxygens are coming from the hydrocarbon. 12 minus 2 is 10, so 10 oxygens must be coming from the O2 molecule. To give us a total of 10 oxygens from the O2 molecule, we're going to put a 5 as its coefficient. Now we have 2 times 5 is 10, plus the 2 from the hydrocarbon makes 12, and that matches up with the 12 oxygens we have on the right-hand side. This is our balanced equation for the combustion of butyric acid. 1 butyric acid plus 5 oxygen makes 4 carbon dioxide and 4 water. Let's look at the combustion of one more hydrocarbon, ethane. In this reaction, again, we've got O2, CO2, and water, so we're still going to approach it the same way. We'll do the CO2 first, then the water, then the O2. The tricky part about this one is that it gives us a fractional coefficient in front of the O2, but we don't want to leave it as a fraction. At the end, we'll multiply all of our coefficients by 2 to get them to be whole number ratios. First, we're going to list out the number of each atom we have on each side of the equation. We have 2 carbons, 6 hydrogens, and 2 oxygens on the left. On the right, we have 1 carbon, 2 hydrogens, and 3 oxygens, just like we do for all of our other combustion reaction equations. We're going to start by putting a number in front of the CO2. Since there are 2 carbons on the left, we put a 2 in front of the CO2 on the right, so now there are 2 carbons on the right. That also changes the number of oxygens, so we have 2 times 2 is 4 from the CO2, plus 1 from the water makes 5. Then we're going to change the number in front of the water so we can update our hydrogens. we have 6 hydrogens on the left, so we put a 3 in front of the water to give us 6 hydrogens on the right. But that also changes our number of oxygens. So now we have 2 times 2 is 4 from the CO2, plus 3 from the water makes 7 oxygens on the right. There is no number that we can put in front of the O2 that's a whole number that would give us exactly 7. If we put a 3 in front of the O2, that would give us 6. If we put a 4 in front of the O2, that would give us 8. Neither of those numbers is 7. Instead, we're going to have to put in a fraction in order to make it balance. The fraction we can put in that will give us 7 oxygen atoms on the left is going to be 7 halves. 7 halves times 2 equals 7, and that matches the 7 oxygens we have on the right-hand side. Now our equation is balanced, but it's not a whole number ratio. To get our coefficients to be whole numbers, we're going to multiply our whole equation, that is all of our coefficients, by 2. 1 times 2 gives us 2, 7 halves times 2 gives us 7, 2 times 2 gives us 4, and 3 times 2 gives us 6. We could update each of our counts, so we have 4, 12, and 14 on each side, but that ratio still holds. Our final balanced equation is 2 ethane plus 7 oxygen makes 4 carbon dioxide plus 6 water. When we write our balanced chemical equations, we want to use the smallest whole number ratio possible. Let's say we were balancing an equation and figured out that 3 nitrogens plus 9 hydrogens yielding 6 ammonias is balanced. We can simplify that equation because each of those numbers is divisible by 3. We do 3 divided by 3 equals 1, 9 divided by 3 equals 3, and 6 divided by 3 equals 2. Therefore, our equation can be simplified to 1 nitrogen plus 3 hydrogens makes 2 ammonias. What are the stoichiometric coefficients required to balance the following equation? C6H14 gas plus O2 gas makes CO2 gas plus H2O liquid. Is the answer A, 1, 19, 6, and 7, B, 1, 7, 6, and 7, C, 2, 19, 12, and 14, or D, 2, 38, 12, and 14? The correct answer is C, 2, 19, 12, and 14. This is going to be very similar to our ethane problem in that we end up with the fractional coefficient in front of the oxygen, and then we multiply the whole equation by 2. Our balanced equation with the fraction is 1 C6H14 plus 19 halves O2 makes 6 CO2 and 7 water. When we multiply by 2, we get 2, 19, 12, and 14 for the coefficients in the equation.